So here, starting the Mac layer, the motivation behind Mac layer is very simple. The fact that, especially in wireless, let's focus here on wireless. The fact that you have one node trying to send to another node, and here we have one node trying to send to another node. If we're talking about wired communication, those two communication can happen with no problem, right? However, when we talk about wireless, it's very challenging because this node sends wireless. It's a broadcast signal to the air, right? So when this node sends a wireless signal, this wireless signal, even though we send the data to this node, but physically what we do is that we send a broadcast signal that goes into the entire environment, which affects the communication that goes from this node to this node. Okay, so even though this one tries to send to this node, however, this transmission affects this node, and at the same time this transmission affects this node. Okay, so in that type of environment, we should control who will have access to the medium at any point in time. That's the purpose of the Mac layer. It's called medium access control. That's this is the issue. This is the main fundamental issue now. So the best way to understand Mac layer is to imagine that we are a group of people sitting in a meeting. This is the best way to really understand all the concepts in Mac layer. So if we are a group of people sitting in a meeting, we have to organize ourselves in any way, in some way, right? Whether we have a moderator who moderates and controls who will talk when, or we can have some side-by-side discussion within the meeting in such a way that does not affect each other. So we need to have some communication between us going on within that meeting, which represents the fact that we are multiple nodes sharing a specific medium. Okay, so the way we organize the access to the medium can be, that's fine. Okay.
Okay. What is the difference between centralized contention-based and distributed contention-based?
As I said, centralized contention-based.
Yeah.
For centralized content, okay, I think we, okay. So particular, it's any type of network, any control access to the medium can be categorized in these categories. Okay. So if we imagine that we are in a meeting and we need to get some communication across, one way is to centralize the control, is to say that we have one moderator of the meeting and he or she will have the control who will talk when. Okay. Or we can say we don't need to have one single moderator. We need to be free to talk, but we'll have some other ways to organize who will talk, and if there is any conflict, we'll deal with it. For example, if you're like in cabinet or something like that, sometimes the cabinet minister controls who will talk when, but sometimes it happens that two members they start to talk, and you cannot get anything from any of them. So we call this collision, that the two people started to talk at the same time, and you cannot really distinguish any of them. Okay, so in that case, we'll we'll deal with that situation. So when that situation happens, we'll deal with it. However, we'll give the freedom to anyone to talk at any point in time. So that's distributed. Okay? So we don't have a single moderator, but we'll allow the distributed control. Anyone can talk at any point in time, and if there is any problem, we'll deal with it. So the centralized can take two types: centralized but contention based, and centralized but schedule based. The problem is that when we talk about contention based, what we mean is that we allow two people to talk at the same time. Okay? Or at least we do not prevent the situation from happening. So it might happen that two people can talk at the same time, even though there is a centralized control. But the centralized controller might try to be more opportunistic, because we'll talk about the drawbacks of having to be everything is scheduled. If everything is scheduled and you miss your schedule, then you lose the chance. Are you following?
Yes.
Okay. But contention based, you may give the access to multiple people with the hope that hopefully those two people, they find a way to talk together, or they kind of try to, everyone says like part of what he wants to say without really conflicting with each other. So in that case, they contend. If multiple people have the possibility to access the channel, then we say that they are in contention. Okay? If more than two people are contending on the channel, there is a possibility that they try to send something on the channel at the exact same instance of time. In that case, we call it a collision situation. Okay? That's more realistic in the case of distributed, more logical in the case of distributed, that basically all the nodes by default have the possibility to access the channel at the same time. So the probability of collision here is higher than here. Although even in some centralized cases, sometimes the centralized controller gives the access to multiple nodes to possibly gain the access to the channel at the same time. One example of this is Wi-Fi. Wi-Fi, even though it's a centralized topology in nature, but it gives access to the nodes to send to or to access the channel at the same time. Okay. So this situation might cause some, as I said, might cause some collision. More than one people are trying to access the channel at the same time. So another approach is to say, I will not allow any collisions. I don't need to have I need to eliminate collisions altogether. Which means that at any point in time, only one person can talk in the meeting. Okay? But if you give the chance to that person to talk in the meeting and nobody else is talking, this person may stay silent for some time. Like, while I'm talking now, I can stay silent for some time, right? Thinking or doing something. During that time, the channel is not used. So that's a waste of resources, right? So you give access to one person and you tell him, the channel will be dedicated for you. And, he's not doing anything, which means that the channel is not utilized during that time. That's a risk. So to give more opportunities will probably lead to better utilization of the channel. But the risk here is collision. Here, you try to eliminate collision by giving less opportunities to access the channel, more controlled and scheduled opportunities to access the channel. But the risk here is that if you give the chance to someone and he does not send anything, that's a waste. Okay? So another branch of scheduled is by saying, if I give access to you and you do not send anything, this is an indication for me that you probably don't have traffic at the moment. So I will reduce your opportunities. So this is the demand assignment. So fixed assignment, I give you access like round robin. Each one will have his turn to talk. I give you the turn to talk, and I have to wait for you until the duration assigned to you finishes. If you have something to say, this would be good because you will utilize the channel. If you don't have anything to say, then this time is wasted. Okay? Or on demand, so as I can do like a quick scan at the beginning. Do you have something to say? Yes or no? Do you have something to say? Yes or no? I get all your demands, and then based on your demands, then I can schedule. Okay? So maybe in the first round, only one needs to send something. In the second round, maybe two. But every time I have to ask everyone. That's an overhead. But at least I eliminated collision, and I did not waste a lot of systems resources or a lot of channel resources by allowing someone to send and he does not have anything to send. Again, all these categories, we'll go through it in more details, but that's the idea behind it. And the best way, as I said, the best way is just to imagine that we are in a meeting, sharing the space, and we want to get some communication across. We want to get some discussion, hopefully useful discussion. Okay? So centralized contention-based, you as a central controller, you want to give access to multiple nodes at the same time so that you make sure that the channel is utilized.
Isn't
But
that
maybe,
the same as the other one?
True, but for the centralized control, you may give access to 2 people out of all the existing ones. And distributed, by default, you give the opportunity to everyone because there's no centralized controller.
So centralized is still more controlled than
Right. Right. So when you give access to 2 or 3 people only, then you sort of minimize the probability of collision implicitly, right? But at the same time, you don't want to make it one so that you reduce the probability of not utilizing the channel. You see what I mean? So that's the idea. I don't know what it's doing. Anyway. Okay. So it's not directly feasible for the case of non-trivial wireless networks where the size is large. If the size is really large, the problem about centralized control is that you have to always connect with this centralized controller in one hub fashion. So you have to have direct communication with this centralized controller. However, this is not feasible and not necessarily possible for the case of wireless mesh network, because for the case of wireless mesh network, as we said before, it's multi-hub in nature. So if the network is large, okay, you cannot have a centralized controller because it's multi-hub. So centralized is not, in general, is not necessarily feasible, especially for wireless mesh networks, where we have multiple hubs in general. So to avoid this, what we could do is that we can divide the large network into smaller clusters. So within that cluster, you can use the centralized, right? So within that smaller networks, you can use the centralized, but from the cluster to the cluster, you use some kind of a distributed control. You have to use some kind of distributed control, right? Especially when the network grows very large, especially from the space point of view, that it's not possible to have one node and you have direct communication with that node. So in that case, you can divide the space into smaller clusters. Within that cluster, everyone has to connect to the cluster head, who can be the centralized control, and then from the one cluster to another, you have to use another centralized, distributed approach. Okay. So it's like, again, we are in a meeting and we can have some round tables. So within each round table, we can have someone to give turns to people and moderate. But when we have some communication from one round table to another, then we have to rely on other mechanisms, which can be distributed or again centralized. But in that case, only the leader of that cluster needs to communicate with the centralized node. Okay, so we have to rely on other mechanisms. Okay, so so for scheduled, what we said is that this schedule can be fixed or can be on demand. Fixed means that we use some kind of time division multiple access, and what we do is that we normally say, okay, from the wireless channel point of view, all the nodes, like you have multiple nodes accessing the same wireless space. So we have one node here, one node centralized node. What this node will do is that it will organize the access to this channel this way. It will say very simply, this is node 1, 2, 3, 4, 5, 6, and so on. So it will say, okay, so this is time slot for node 1, this is time slot for node 2, this is time slot for node 3, 4, 5, 6, and then 1, 2, and so on. Very simple, right? So this time slot will be assigned to node 1. So only node 1 can send any traffic within that wireless space. So if I organize it this way, I guarantee that there is no collision, because during that time the channel is only dedicated for one person. Very simple, fixed, and that's it. Again, the risk here is that node 2 at this point in time does not have anything to send. Channel is wasted. That's the risk. Okay, so that's what we call a TDMA. Very simple, fixed. Same thing can happen for, instead of dividing the time, because we know that signal in general, any signal, whether wireless or wired or anything, or any electrical signal or electromagnetic signal, has three different characteristics. It has the time aspect, and it has some frequency response, right? So you know, like any signal has some frequency response. So the signal itself exists, or we can move the signal representation into the frequency domain, right? And it has like certain phase shift. If it's a periodic signal, it has some phase shift. So we take all these three characteristics, and we can divide the channel based on these dimensions. So we can say that instead of dividing the channel, the common channel, into time, we'll divide the common channel into frequency, which means that we will divide the environment into frequency subchannels. All the nodes can send at the same time, but on different frequency. An example of this is just like radio channels, FM or AM or something, right? So if you want to listen to any channel, you just tune to a specific frequency and listen to that channel. So if you want to talk to a particular node, just switch your frequency on your transceiver towards this frequency and receive the signal from that node. Same thing. Or CDMA, which we will talk about it. Instead of dividing as time or dividing as frequency, we divide the channel using what we call orthogonal codes, okay, which we will talk about. So if that division or that schedule is fixed, then we run into the risk of losing the opportunity or wasting the channel resources. So we can use some kind of on-demand, but on-demand has some kind of overhead, but in the sense that every time I have to ask you, okay, what do you need? What do you need? I have to always ask you, what do you need? Or I can just pull. Do you have anything to send? Do you have anything to send? And so on. So on-demand always has like some incremental overhead. But in both cases, I eliminated collision. There's no collision because it's scheduled. Schedule eliminates collision altogether, because I should never have a situation where I allow two people to access the channel at the same time. Okay. Contention-based has the risk of colliding. So multiple people access the channel at the same time. So the wireless signal from two nodes reach to the receiver at the same time, at the same frequency. So the receiver will receive just noise. The receiving node will receive just noise. Okay? And it will not, the transceiver of the receiving node will not be able to distinguish between the two signals. So we call that collision. And collision, an important comment about collision always happens at the receiver. Collision happens when the transceiver at the receiver side receives both wireless signals superimposed on each other. So you receive a composite signal. This is not the signal from A and not the signal from B. This is a composite signal. You can think of it as the summation of the two signals. But the summation here is a complex summation. Summation in the frequency and in the time, and the phase shift. So you receive a deformed signal. You will not be able to detect one signal from the other. Okay. So hopefully by that we can eliminate, or so we can save the coordination overhead, because we said that if we schedule on demand and stuff, we can run into some overhead. But on the other side, we run into the risk of collision. And in many cases, in these scenarios, we use some kind of randomization. So nodes will send, and they do not have anything to control them. So how would I know that somebody on Earth wants to send, so I cannot send? How would I know that in a distributed way without a coordinator telling me? Okay. In many cases, we use some kind of randomization techniques. So we say, if you want to send, generate a random number and wait for a specific time and then send. Okay. So hopefully, if two nodes are generating random numbers, hopefully they will generate different random numbers, in which case they send at two different times. Hopefully. But again, this is not a guarantee. They can actually send at the same time, and then collision will happen. We're not claiming that we will get rid of collision. Collision will happen here, no matter what you do. Okay? But at least by using some kind of randomization techniques, we can sort of reduce. So that the challenge here is always to find techniques to try to reduce that collision as much as possible, but not to eliminate it. No matter what you do in that category, you will always have collision. The only way to eliminate collision altogether is by having to organize, having to be very strict on who will access the channel.
Why don't they queue the requests instead?
They do.
For contention.
Remember,
For in contention base, instead of randomizing, why don't they just queue the requests?
every node has to queue their transmission anyway. But remember, we're talking about a network. We're talking about multiple nodes sharing a particular wireless space. Okay, this is not one machine, and we don't have the situation that we have processes inside one machine. No, this is a network. It's a distributed network. So each node does queue all the traffic into its buffer. Okay, but there is a time that it needs to send this across the network, and we're sharing the wireless medium. So when can I send? So if I send and another node sends at the same time, and we're sharing the wireless space cannot queue the two requests. It cannot happen. Okay, unless we're sending to one node using wired, and then this node will send it using wireless. So in that case, it's not wireless. So this is the challenge here: is that the wireless space is not a physical thing that can queue or buffer requests. See what I mean? So this is the challenge here. Randomization is proven to be efficient in that situation, and you will see why. In many situations, randomization can work and can give you good performance. Why? Okay, so for the distributed case, we don't have any centralized control. It's distributed in nature, which means that in a scenario like this, any of these nodes can send to any of these nodes at any point in time. Okay? So one possibility is just to use what we call Aloha. Aloha was actually the first mechanism for channel access that does not require any kind of centralized control. And the idea of Aloha is just very simple. Any of these nodes wants to send, just send. Okay? We don't do anything. It's like we are in a meeting and everything is just messed up. Anyone wants to speak at any point in time, just speak. And then if it happens that two people speak at the same time, we'll deal with it. We'll see what to do. Okay? And as you can imagine, the amount of useful information that you can get in this environment will typically be low, right? Because you will run into a situation that it happens so many times, very frequently, that two people or three people talk at the same time, in which case none of their speech will mean anything. Okay? So in order to imagine Aloha is like, especially because we are in Doha, I always explain it to my students using roundabouts. This is the best way to understand the Aloha protocol. Okay, assuming that we have people with very bad behavior, they get into that, which happens very often as we can experience. So people get to the roundabout and they just go. They don't even wait to see if there is anybody else who's getting into the roundabout. They just go through the roundabout. What is the advantage of this? Despite the simplicity and the fact that it might sound illogical, but it has a very important advantage. In order to appreciate this advantage, 10 years back, in Doha was full of roundabouts, right? Why? Because people didn't have to stop. Whenever they want to go through any intersection, they just go through roundabout. They don't have to wait for signals. So why did that work in the past but not now?
Less population.
Less population, bravo. So it was very efficient if the load on the network is low, because you didn't have to wait. Whenever you want to send, just send. You don't have to go through any kind of overhead. You don't have to split your traffic within a specific frequency or time or something like that. You don't have to wait for your slot. So if the network has low load, usually this protocol works perfectly because you don't have any overhead. So the most important thing about this mechanism is that it has almost zero overhead. Okay, you don't have to coordinate anything. You don't have to incur any overhead to coordinate anything. Okay, so this is the simplest way. We're not dividing. We're not assigning any resources, scheduling, or it's just distributed. And if the network is high, if the network has high load, high traffic, which is the situation that we have now in Doha, these roundabouts become, miserable, right? The performance on these roundabouts becomes a real issue from multiple aspects. Because when the traffic is high, the possibility of collision becomes high, right? Okay, so let's just have a little bit of coordination. Let's add an extra step. So we call it carrier sense multiple access. So before you get into the roundabout, please just see if somebody else is inside. Okay? So that's what's supposed to happen. Though it doesn't happen 100%, but that's what's supposed to happen. Carrier sense multiply. Carrier sense means sense, just sense, listen. Before you talk, just listen. Okay? So if we are in a meeting, I want to talk. Listen, is somebody else is talking? No. Okay, so I will talk. I will talk. I will not raise my hand to talk. No, I will talk. Okay? So in that case, I will eliminate collision, of course. Not eliminate, sorry. I will reduce slightly the collision, of course, because if we imagine the roundabout and we get into the roundabout, then if I listen or if I see somebody else inside the roundabout, I will stop, right? So I will reduce the collision a little bit. I will not eliminate it. Why? Because I listen, nobody's talking. Somebody else might be listening at the exact same time. So he and I might take the same decision to talk at the same time. So listening will help me because the transmission by nature is asynchronous. It's not synchronized at specific time slots. Okay? So somebody might be sending, and when I listen during the time that he's sending. But if we, at any point in time, decide to send at the same time, collision will still happen. So carrier sense will reduce but not eliminate collision. Okay? Okay. So this scenario here uses carrier sense. And it's distributed in nature. And if we think about wireless mesh network, then we have some interesting scenarios that we need to talk about in this network. Wireless mesh network talks about the fact that we have multiple hubs. This simple scenario shows multiple hubs, right? So you have 1, 2, 3 hubs. These circles represent the fact that if any node wants to send, this is the transmission domain. because again we send a wireless signal, it gets broadcast in the air, right? So if this node sends, anyone in this area, anyone in this circle will be able to listen to that signal. Okay, so this is the transmission domain of that signal. So carrier sense means that when A wants to send anything, it should listen. If there is a specific transmission happening, in that case, it will be from B, right? If B sends anything, C and A will listen to it, right? Because they are within the circle. Are you following that? Okay. If C sends anything, B and D will listen to it because they are within the circle. Okay, كده? So there is a very interesting scenario that might happen here, which we call it hidden terminal problem, and that happens specifically and very commonly in the case of wireless mesh network. And that's the motivation for us, that for wireless mesh network, all the techniques that we talked about so far will not work efficiently. That's the motivation, that we do need more techniques in the case of wireless mesh networks. Okay? So if A wants to send to B, just listen, nobody else is talking, it will send. Who can listen to this transmission? Only B. A wants to send to B, so that's fine. Will C listen to that transmission or not?
Yes.
C will listen to the transmission that's happening from A to B.
I mean, it's in the circle, so I can hear it.
In the circle of what? C. Can it listen to the signal going from A to B or not? B, is it in the circle of A?
Yes.
C. B, yes. C, is it in the circle of A?
But there is a common circle in the middle.
That's this common circle here.
That's
is
only
for
B?
B, yes.
I see.
This is for the signal going from B. This is for the signal going from A.
Okay.
This is for the signal going from C, and this is for the signal going from D. That's how, okay? So if A wants to send to B, C is outside of the circle. So C will not feel anything, right? C wants to send. It will listen, right? It will listen before it sends. Is there anyone sending?
It will not hear.
Okay, it will not hear. That's the key. Why? Because the transmission from A to B is away from C. In other words, C is hidden terminal for the transmission happening from A to B. So using Sigma CA, using the carrier sense, C will not hear anything. So in that case, if it wants to send, it will send. Okay, it will send to B. This is the situation that we say A is a collision. Because during the transmission that's happening from A to B, C is hidden, so C will not listen, so C will send to B. And the collision will happen. So in that case, we have a collision here. What is the implication of this? B will not be able to recover neither the data from A nor the data from C, even if the overlap between the two transmissions is 1 millisecond. So in other words, if you have the transmission from A to B starts here, starts at this time, T1, and it lasted until T2. Okay? If the transmission from C to B happens at T2 minus delta, here, okay? This is T3. If the transmission from C to B happens at T2 minus delta, so this is delta, this is a collision. Even though it's a very simple overlap, it's a small overlap between the two transmissions. But this small overlap will cause the fact that B will not be able to recover this data or this data. Why? Because at the end of the day, it deals with analog signal. In order to get the data, I have to recover the analog signal as is and then convert it to the digital domain. If I have one part of this analog signal corrupted, I cannot recover this data. That's it. Okay? So this scenario is what we call a hidden terminal problem. And this, as you can see, this happens specifically in the case of multi-hop, where we have multiple hops here. So this scenario is less common in scenarios in cases like Wi-Fi. If we have one access point and everybody's sending to the access point, this scenario happens less often. It still happens, but less often. Okay. But in the case of wireless mesh network, where you have multiple hops, especially in large networks, this scenario happens a lot. Okay, so that's one interesting scenario that we need to find solution for. And as I said, this is one of the motivations why we do need new mechanisms, especially in the case of wireless mesh network. Another scenario which is interesting. In that scenario, there's no collision, but let's see what happens. B wants to send to A, okay? So in that case, this transmission, B, no one is sending anything, so clearly B can send, right? When this transmission happens, who can listen to it? Anyone within the circle, right? So A will hear it, and C will hear it. So both A and C will hear it. What is the reaction for you to hear any transmission? You wait. Imagine that C wants to send to D. C wants to send to D.
B will also hear it.
B will also hear it, that's true. So the question is, will that transmission happen? And if it happens, does it cause any problem?
No.
If it happens, it should not cause any problem, right? Because if C wants to send to D, B will hear it, but does B care? B is not receiving that packet, is not interested in receiving that packet. And B is sending. The collision happens at the receiver, not at the sender. So if C wants to send to D and B hears it, B will not care. So this transmission should happen smoothly, and it should not cause any problem. But let me repeat the first question. Will that transmission happen?
It depends. Does B know that C wants to send to D, or does it know that C wants to send?
Oh, the question is from C side, not from B, because B started the transmission already. Once B starts the transmission,
Uh-huh.
there's no way back.
So
I'm done.
C knows
C.
that B is sending to A.
Yes. So C will not send. Okay. That's a loss of a transmission opportunity, which happens because of the carrier sense multiple access. And this happens why? Because C hears that B is transmitting, and it does not have any contextual perspective about the network to know that D is away from B, so I can send to D. It doesn't have any location information or any special information that allows it to say, oh, even though B is sending, but my transmission should not affect it. It doesn't have this information. For using carrier sense multiple access only, it will not have this information. So it will abstain from sending, whereas it should actually send, and this transmission should not cause any problem. This scenario, we call it exposed terminal problem. We call it exposed terminal problem because C is exposed to B. Because of the fact that C is exposed to B, this will allow it not to transmit, whereas it should actually transmit. Okay, so those two interesting scenarios happen a lot in especially in wireless mesh network, where you have distributed nodes in nature using multi-hop scenario. These scenarios are the motivation for us that the normal mechanisms that we used to use for the case of one-hop wireless networks, these will not work necessarily efficient for the case of wireless mesh networks. So we need to look for other mechanisms. So these mechanisms, by the way, are fundamental, these are basic concepts in wired and wireless networks. So the Aloha and the carrier sense actually will have the chance to analyze the performance of some of these. We did, I think, in wireless communication, right? Yeah. So we'll not talk about this in details in this course, but in other courses we actually get to the calculation of the efficiency and the performance of some of these mechanisms in details using some mathematical equations. So the idea here is that Aloha has very low efficiency in certain loads. Carrier sense multiple access need is designed to overcome this limitation in high loads, but even in the case of wireless mesh network, it actually performs bad in many cases. So now we need to, in order to avoid the hidden terminal problem, we need a node that starts receiving the data or the signal from another node to inform everybody around it. Please, I'm receiving something. Do not send me anything. Because if that's the case, in order to avoid going back, we'll just draw the scenario again. So A. Are you sure? But this is for this slide, not for the entire okay, we'll see how it works. Okay, it will be because of you. Anyway, so what we need to do now is that when A starts to send to B, B right away needs to inform everybody around it. Please, I'm receiving something. Do not send me anything. Okay. So this could happen using two scenarios. The receiver, once it starts or while it starts receiving something, it should right away inform others by sending out a signal indicating that it's receiving something. This means that B, once it starts receiving something, it needs to send something. Okay? We call that a busy tone protocol. But just imagine, I'm receiving a signal and I want to send a busy signal. How can this happen? سؤال لك هلا. And different frequency, بالضبط. So the only way for me to achieve this is by using two different frequencies. So the data transmission happens within the normal channel frequency, and then there is like a busy tone signal which can use another frequency range. So while I'm receiving on this frequency, I can send a busy tone signal. It's just a control signal to indicate that right now I'm receiving something, please do not send me anything at the same time. If we do that, then we can eliminate the hidden terminal problem, right? So this will require some kind of an overhead to have to send this busy signal. So every time you receive something, while you are receiving, you have to have a busy tone signal during the entire time. I'm busy, I'm busy, I'm busy. You send it on a different frequency. So before you transmit anything to B, you need to listen to the busy tone frequency. If the busy tone frequency has some signal, then B is busy, do not send it anything. So, of course, this requires some kind of an overhead, and it uses a separate frequency range for the busy tone, which is costly. Another approach is that before you send something to B, which is the more common scenario or the more common mechanism that's currently used in 802.11. Before you send to B, send before that a request. I want to send to B something. B will respond back saying you can send. When B sends the response back, C will hear it. It's similar to the busy tone, but it happens before the transmission, not during the transmission. Okay? So before the transmission happens, inform the interferers, which is C in that case, the hidden terminals, that I'm expecting to receive something now, so please do not send me anything before the transmission happens. So there is some time synchronization in that case. This is how it looks in the time domain. So this is A, B, C, and D. So if B wants to send to C something, this happens using 4 different steps. Yes, this is the cost in wireless. This is how you have to do it in wireless, unfortunately. So B, before it sends anything to C, it should send what we call request to send. Request to send is like a small control frame. It's not data. Remember, data will last for a long duration, but this is like a very small frame. It takes less than 1 millisecond. It will send request to send to C, okay? And then C, in that case, will send clear to send. So those short control messages happen before the transmission. They are very short, and they happen before the actual data transmission. The benefit of this is that both A and D are now prepared for that transmission that's happening from B to C. Right? Because A listened to the request to send. In that case, A will start preparing itself for that transmission. Luckily, these control frames will also have the duration of the data. So A can now prepare itself for the fact that it knows that we have a duration of RTS, which is fixed, duration of CTS, which is fixed, and duration of data, which is variable, but luckily I have this duration in the RTS, and the duration of the acknowledgement, which is also fixed. So the only variable thing here is data, and I have the duration of the data inside the RTS. So I can calculate the time that I have to wait before I start listening again on the channel.
So that's what wireless networks do right now?
Yes. For the case of ad hoc. For the case of infrastructure, this is called Mecca, and this version or this variation of Wi-Fi is not activated by default. It's not activated in the wireless card by default. So by default, it doesn't use RTS CTS.
What's the default then?
The default is non-RTS, the normal MAC. So there is collision, but it doesn't actually address the issue of hidden terminal problem, because it assumes that there is an access point, and this scenario of hidden terminal problem does not happen very often.
CSMA, you mean? The default?
Yes. The default is Cisma CA. Yes, you're right. Okay. So you have to turn on RTS CTS if you want to use ad hoc, or if you want to have RTS CTS. Okay. So all the nodes that are not involved in the transmission, they calculate what we call network access vector, or it's nothing but like time. It calculates a certain time. During this time, it's idle. It's not doing anything. It just goes to, actually, if it's a sensor node, it can go to sleep during that entire time. Doesn't do anything. Okay. So once I listen to RTS or CTS, I have to calculate the nav and wait. So now the question is, does this eliminate collision? Well, certainly it
Sorry. Over here, B and C are communicating. Right? B is sending to C. A and D are still free, so A and D can communicate at the same time?
Well, remember that A is not in the range of D at all.
If it was.
Assume
that it was.
If it's a circle or something, if it's
especially A is close to
okay.
D.
If A wants to send to D, wallahi, that's a good question. If A wants to send to D, well, normally using that scenario here, by default A and D will go into nav, so they will not be able to send to each other. Using this particular mechanism, even if they have data to send to each other, and even if their transmission does not affect B and C, they will not. Because A will listen to RTS, D will listen to CTS, so right away they will abstain from sending anything to each other. Okay? But that's an interesting...
What if they are not waiting for RTS and CTS?
If they are not waiting?
Yeah.
There is a hidden terminal problem. If they are not waiting for RTS CTS, okay. So let's see. That's an interesting question. Let's see. If we are not in the RTS CTS mode, and we have,
then they will do the CSMA.
We have.
It will be the same as CSMA.
CSMA, right? Let's see. B, C, and assume that, I don't know, like how would you represent A and D, but assume that A and D. It would be something like this, because A and D have to be in the transmission range of each other, right? So if B wants to send to C, B will send. Okay? Who will listen to it? Assume that A will listen to it, of course. Okay? So A will not send anything using Sigma CA, no RTS. Okay? So A will not send anything. Okay? If D wants to send to A, D can send to A. Because D, if it does not listen to the transmission going from B to C, assuming that D is outside of the range of B, assuming that the range of B is like this, A will listen, but D will not listen. Okay? So D will send. The question here, is there any collision in that scenario?
Yeah, we'll be C.
Huh?
With C.
With A. Collision at A.
Okay, so let's put the transmission ranges, because depending on the transmission range, the collision might happen actually in both A and C. Okay, so the transmission range of D certainly spans A. In that case, it will span C. The transmission range of B is like this. The transmission range of A is not sending, so we don't care. So certainly the transmission from D to A will certainly reach C. So there is a collision in C. Okay? And the transmission from B to C will definitely reach to A, because A is within the circle. So definitely there is a collision in B. In A, sorry. Right?
So the transmissions cannot be sent to a specific node. They just have to be broadcasted.
Oh yes.
They cannot be
This is wireless.
specified.
This is
Like-
wireless. Unless the only exception to this is what? Can someone
use different frequencies?
different frequencies, right? Okay. Yeah, but within that frequency, also when you send something, the wireless signal will be broadcast. Okay. What is the exception to this? If you use some kind of directional antenna, which is used in cellular networks very often. But the default, all our devices, all these use some kind of omnidirectional antenna, so it's broadcast. So of course we use the idealistic view here, but usually the range of electromagnetics around this is not homogeneous. So it's not actually circle. To tell you the truth, it's not actually circle. But here we use circle for simplicity. But the electromagnetic pattern around this is more complicated.
What is it like?
First of all, it's 3D. Okay, and it's not a sphere. It doesn't have to be a sphere. Sometimes it's like this. It depends on what type of antenna you're using. It's not. This is the idealistic view of it. To represent it using a circle, this is idealistic. But in practice, it's more complicated than that. There is like conic antenna, there is dipole antenna, there are all sorts of. Actually, this one uses even more. It uses like some kind of antenna arrays and multiple. And yeah, it's very complicated. But anyway, this is for simplicity. Okay. So any more questions? So that's the. That's how you. Actually, this is a good exercise that we can build on it. Yeah. So the question is, does this actually eliminate collision? Let's see. Of course, here the answer is no. RTS CTS unfortunately reduces but not eliminate collision. In other words, a scenario like this where A wants to send to B and D wants to send to C. Okay? So B receives the RTS from A. So B will send CTS. CTS can be listened to by C. Okay? But D is a hidden terminal with respect to CTS. So, so D is away from the transmission range from B to C. Okay? So now it's starting to get more and more complicated. So because D is hidden, D will send RTS. If D wants to send to C, D will send RTS. Okay? So the first collision that will happen is at C, that there is a collision between the CTS and RTS. What is the effect of this collision? Well, the effect of this collision is that D will not get CTS, in which case it should not start sending data, right? Because C has collision here, so C will not be able to recover this RTS. As a result, it will not send CTS.
C will have collision, but B will have...
Yeah, B will still continue. Yeah, will continue.
Yeah.
Okay. So C has collision, it will not send CTS, in which case D will try again. Okay, because it did not receive CTS within a specific timeout, it will try again. B is not affected by this because A received the CTS, so it should send the data. Data is very long, as you can see, in terms of time, it's very long. It will go for some time. During that time, you are vulnerable. Collision may happen at any point in time. This is the vulnerable time now. So D sends RTS. In that case, no one is no collision. So C will say, okay, I will send RTS. And why is that? Because remember that C here did not go into nav state, because it was not able to receive this RTS. Here, the C here should, once it receives this, it should get into nav. If C here performs nav, it should not send CTS here. صح? صح? So this CTS, if C receives RTS, then it should send nav unless it's not the receiver. Yes, unless it's not the actual receiver of that RTS. The idea is that when you receive an RTS, then you ask yourself, is this RTS is for you or for somebody else? If it's for you, then you send CTS. If it's for somebody else, then you go into nav. Nav is the wait time. You go into an idle time.
So why didn't C go into nav?
Because you are the receiver.
No, I mean, why didn't it go into nav when A is sending to B? Is C
Right,
not
because
in the range
yes,
of
because
A?
yeah, I'll tell you why. Because when C receives the CTS, it received at the same time RTS. So this
C,
CTS
yeah.
is not recovered.
C is not in the range of A then.
Yes, of course, it's not in the range of A. No. I think you are a bit confused. This is the special context of this. A cannot be in the range of C. A cannot be in the range of D. Every one of these, A is in the range of B. B is in the range of A and C.
Okay.
Okay? Let's agree on that.
We mixed them up before.
Yes.
So B sent here to send to both A of A and C at the same time?
Yes. But unfortunately, A will not recover CTS as a result, it will not go into nav, right? And this RTS collided with the CTS. So RTS will come, I will ask myself, am I the receiver? Yes, so I cannot go into nav. I will send back CTS, which will collide with the data. So here there are no collisions. There are, two collisions. I said no collision, sorry. There are two collisions. One in the control packets and another one with the data. So even though here the collision happens between data and CTS, okay, B will not be able to recover either. This whole data is wasted, and CTS is not heard, in which case B will not get into nav.
Okay, C here.
That's rather a complicated scenario.
Yeah, C did not send the request to send to B.
Say again?
C did not send request to send.
No, C does not want to send anything. Request to send goes from a node that wants to initiate a specific transmission.
Yeah, so why B send clear to send to C?
B sends a clear to send as a broadcast. Everybody in the range will be able to listen to it. In that case, both A and C will listen to it. A is the one that's required to receive CTS and absorb it. C, this is great because C will listen to it. It should not absorb this CTS, but it should understand from the fact that since this is CTS, I need to go into nav because I should not be involved in this transmission. So
if CTS is not for C, C should go to nav.
if the CTS
Not belong to C. CTS is in the CTS.
Yes, CTS should go into nav, right? However, CTS was not able to recover this CTS because of the collision.
In case of no collision at C.
Yes, of course.
CTS.
Yes.
Why did C go to nav? CTS is not for C.
Yes, that's why C should go to nav.
Why?
Because it's not part of the transmission. Otherwise, if it does not go into nav, this means that there is a chance that C can send anything during that time. Nav is an indication for the node that I should not do any, I should stay idle during that particular time. Actually, if it wasn't for this RTS, C would have turned into nav, in which case during this entire period it should stay idle completely. Even if it receives anything from D, it will ignore it. During the state of nav, if you receive anything from anyone, you will totally ignore it, discard it. Okay?
Okay, one question here. The signal of CTS or RTS is like broadcasted. It doesn't.
Yes, of course.
So anyone can receive it.
Yes.
Even,
anyone in the range can receive it. Anyone in the range will receive it. Only one will absorb it, the one who has the address that's in this RTS or CTS.
So there is specification of
Yes,
RTS.
of course. The RTS is a data frame. It's very short. All it has is the fact that this is coming from the source node X to node Y, and this is to inform node Y that there is data coming with a specific duration. Okay, so this is a preparation for the data. For every frame of these, there has to be source node address, destination node address. Okay, so that's why here it's red, here it's gray. Gray means that C is not the destination of this frame, but it will listen to it.
Yeah, but this means we will not solve the hidden problem. We still have the hidden problem.
Of course.
Should RTS solve the hidden problem?
Well, that's what I said. I said, does it actually? Well, it solves it partially. Because the scenario that we talked about before is clearly solved. Yani, the scenario of, let's see, scenario we have A and B and C. This is the basic hidden terminal problem. This is A, B, and C. Okay? So now A wants to send to B. A will not send the data right away. It will send a very short frame to inform B that I want to send you something. The idea here is that because of the fact that this control frame is very short, that reduces the possibility of collision. And instead of sending the whole data, because the whole data maybe spans, I don't know, like tenths of milliseconds. And during that 10 millisecond or 20 millisecond, you are vulnerable. Collision can happen at any point in time. But instead of doing that, instead of taking the risk of sending this huge data and have 1 millisecond overlap which wastes the whole data, just prepare everyone to the fact that you are sending this long frame by sending a short control frame. So A will send RTS first. Okay? B, as a result, will send CTS. CTS will be distant to A, but C will listen to it. The hope here is that this RTS and CTS will be fast enough, because they are very short, right? That it will happen and it will inform C before C starts sending anything to B. Because of the fact that this RTS and CTS frames are very short, that reduces, not eliminates, reduces the possibility of collision. But if it happens that while you're sending RTS, C starts the transmission right away by sending RTS. So while you're sending RTS, C is hidden from that RTS. So if it sends RTS, collision will still happen.
So if A sends the RTS and completes sending it, and B hasn't sent the CTS yet, and meanwhile C sent another RTS.
That's
to
the
B,
scenario that we talked about.
then
here.
it's fine. It would work.
No.
It won't.
No, it won't.
Okay.
It won't. But the collision will not happen.
Yeah.
In that case,
Then.
between RTS and the CTS, the collision will certainly happen after that, when the two data start. Yes.
What if they're not in the same time?
Yeah, if they are not in the same time, RTS and CTS will be working fine. However, the data will then have some kind of overlap. Any overlap between the two data getting sent to B, the collision will still happen.
So you're sure that there will be a data overlap? Even
Of course, if the RTS and the CTS they have no overlap, in which case they will work in informing B that there is some data coming, then the problem here is that if B is the destination of this frame, it's obligated to send CTS. There is an obligation that B has to send CTS, in which case C will start sending, A will start sending, and the collision will still happen. Even if there is small overlap in the data. So again, having RTS CTS reduces the possibility of collision, but it does not eliminate. And that's why, otherwise, if it eliminates, then this mechanism should be categorized under non-collision based protocols. But here the collision will never be eliminated as long as you do not have a schedule-based transmission. Only way to eliminate collision is by having a schedule-based transmission. Okay, so we have 5 minutes, and so the MAC layer differences in the case of wireless mesh network, they have some fundamental differences. MACs for wireless mesh networks are concerned with more than one hop communication, and that creates the challenge of hidden terminal problem and exposed terminal problem, and the fact that you have to deal with RTS, CTS, and so on. So that implies the fact that MAC has to be distributed in nature. Centralized is not an option in many cases, with the only exception of cluster. If you can form some clusters in your mesh network, then yeah, you can get by using some kind of centralized approaches. But usually, distributed approaches are the one. And you have to facilitate multi-point to multi-point, which means that in general, nodes are organized like this. So you have nodes like this, and for any point in time, you have to support the fact that this node can send here, this node can send here, this node can send here, and at the same time this node can send here, or this node can send here, or this node can send here. So these all these nodes are connected in some kind of a mesh, so multiple points can communicate with one single point, or one single point can communicate with multiple points, which means that you have multi-point to multi-point transmission. Go ahead.
Were you just implying that a node can receive and send in the same
No,
time?
I'm not implying that, but
So it cannot?
it depends. We'll talk about that in a minute. It depends. Okay. So network has to be self-organized, which is the feature that we talked about before in mesh networks, because all the hubs are wireless. So a node should be able to discover all the nodes around it. And based on that, it should self-organize itself based on the topology that's existing at the moment. And use that information to better collaborate with others to transmit efficiently. In addition to this, if we're talking about mobile ad hoc networks or mesh network where the nodes are mobile, that creates even more challenges, right? Because the topology in that case will be very dynamic. As the nodes move around, the topology will be changing a lot. So imagine RTS and CTS and all of this, and we're talking about fixed nodes. So you see all these scenarios and all these complicated issues that happen while the nodes are fixed. So imagine if these nodes are mobile, the range is dynamic, the range of transmission gets changed, and based on that, the topology of the network is dynamic. That creates a lot of challenge. Okay. So the improvement when it comes to wireless mesh network comes initially by saying, okay, so we have one single transceiver. One single transceiver means that you have one antenna and one baseband transceiver, which means that you can adjust this transceiver to communicate on different frequency. Okay? But you have to use one single frequency at a time. You can change, but you have one single frequency to work during a specific time. The other variation of this is that if we have a very complicated circuit that has multiple transceivers, each transceiver has its own antenna, that answers your question. That in that case, we can send and receive at the same time. Not only that, we can send on two different frequencies at the same time, okay, from one node. So one transceiver can be used for receiving on a specific frequency, the other transceiver could be sending on other frequency. I could be using 3 frequencies at the same time. But of course, this comes with a cost, right? So the more transceivers I have, the more complicated the circuit will be, the more power consumption that will have, and that creates all kind of effects on the cost, on the energy consumption, on different things. Okay. So imagine that we want to use the existing wireless nodes We don't want to reinvent the wheel. We don't want to invent things from scratch. And we need to have some incremental improvement given the node design that we have to work efficiently for the case of wireless mesh network. So one thing we did is that we said, okay, we'll increment the existing protocols by introducing MACA or RTS-CTS. So that will improve a little bit by reducing collision. And it will facilitate, in a way, the fact that we have distributed environment, right? Another type of improvement is by saying, let's change the channel that we use for transmission dynamically. In other words, we said that the challenge for like two nodes like this and two nodes like this, if this node wants to send to this node and this node wants to send to this node, those two transmissions will not happen at the same time, right? And this node will, the signal coming from this node to this node will actually reach here, in which case you can have collision. So here what we're saying is that, okay, let's dynamically change the channel where these transmissions are happening. So if we assume that this transmission uses channel 1, this uses channel 2, if we can do that, then we can allow those two transmissions to happen at the same time, right? So this collision will not happen because they are on two different frequencies. So this node will receive two signals on two different frequencies. There's no collision, okay? Because its transceiver is adjusted to receive from that channel, not from that channel. So this channel for it's gonna be nothing. It's like you're listening to FM channel 1, but you're still receiving all the other channels at the same time. But you're tuned to that particular channel. So you will listen to this, and all the other ones will be nothing to you. There will not be even noise. Okay, so so we can utilize this this idea, especially in wireless mesh networks, to facilitate multiple transmissions to happen at the same time. So first, we're using RTS-CTS, but remember, RTS-CTS are in-band signals, which means that they happen in the same frequency where the data transmission happens, right? If we change to a different channel, then we can allow multiple transmissions to happen in parallel. Let's think of it as two parallel transmissions. If we go back to our meeting, so we can assume that two people are using two different tones or two different voices or two different languages. So the two conversations are happening at the same time, but they are not affecting each other at all. Okay. What is the effect of this? Well, there is a clear overhead now that changing this channel dynamically has certain implications. First, it requires that you need to have some kind of an overhead to manage who should be tuned to which channel at a specific point in time. That's not an easy job. This is very complicated.
And you can have like million or hundred of channels. Right?
Of course.
Yeah, so you need to scan them all.
Not only that, usually you have in one transceiver, you can have 5 channels, 6 channels. Actually, in 802.11a, you have 13 channels, 13 non-overlapping channels. You can have more than 50 or 60 overlapping channels. So you can tune to different channels at different points in time. But remember that you have some constraints. You need to tune to a particular channel where you are expecting the other node to send you data at any point in time. For example, if a node is tuned to channel X for receiving, and it has one transceiver, so it can use that transceiver for receiving or for sending at any point in time. And whether for receiving or sending, it's one channel at this point in time. If you tune to channel X and somebody is trying to send you data on channel Y, tough luck. You will not be able to receive anything. So this creates the channel of having to have like some kind of synchronization. So you have to tune to the channel that you're expecting someone to send you on this channel. How do you do this? Remember, we are totally distributed. In that case, we have to resort to some kind of predefined schedule. But schedule not for the time for the channel. So we will have some kind of predefined schedule, so that if you know that at this point you and other node Y in the network will be tuned to the same channel, this means that you can communicate during that particular time. In that case, you can use the buffer inside the node to buffer the traffic, and then once you tune to the same channel like other node, then and only then you can send that traffic. Otherwise, you keep it in the buffer. So that's how we do that. So the solutions like RTS and CTS and all of this achieves low end-to-end throughput because they reduce the amount of collision, but again, they do not eliminate it. And especially for the case of distributed wireless mesh network, as we have seen, there are very complicated scenarios in which collision will still happen and with high probability. So the bottom line is that as long as collision or contention occurs frequently, whichever way you use, the performance increments will be small. So for the case of multiple channel and single transceiver, you have some degree of freedom of changing the channel, but at any point in time you have to be tuned to one channel. So in that case, the cost is reduced because you only have one transceiver, so your circuit design is not very complicated, right? But you added the possibility of changing dynamically the channel. So in that case, different nodes may operate on different channels simultaneously. And that will facilitate 2 or 3 transmissions to happen at the same time. There is a paper which I have actually submitted today on Blackboard, and the idea of this paper is very simple. Is to leave the 802.11 MAC layer as is, and then it creates some kind of they call it seed slotted channel hopping. Seed slotted channel hopping. A channel hopping mechanism which allows any node to have a particular schedule of hopping between one channel to another. This hopping is controlled by a sublayer on top of 802.11. So 802.11 is not touched. This is the advantage of this node. It's just there is an intelligent layer on top of 802.11 which tells it, at this point work with channel X, at this point work with channel Y. and I'm adjusting these channels X and Y and Z in such a way that guarantees certain constraints or certain performance metrics. These performance metrics include the fact that I should never have the situation that node X is sending me something on this channel and I'm not listening to it. I should always have some kind of overlap channel with every single neighbor around me at any point in time. Otherwise, I will not be able to communicate with them. Like if you have a node like this, and it has 3 or 4 neighbors, this node should have a specific channel schedule, okay, in such a way that allows it to have an overlap with this one at one point, and this one at one point, and this one at one point, and this one at one point. Otherwise, if you do not have an overlap with any of these nodes, you can never communicate. It's like you don't have any link. Okay? But you have to have an overlap. However, you don't have to have an overlap in the entire time domain. You can have only partial overlap, which allows you to have even sometimes transmission between this node and this node, and between this node and this node. And those two transmissions happen at 2 different channels at the same time. Okay? So there are certain constraints which are taken into account to support this seed slotted channel hopping. It's nothing but, as I said, a sublayer on top of 802.11. It doesn't touch the actual implementation of 802.11. It's just something on top of it that tells it, at this point in time, use channel X. This schedule, by the way, it's proven in the paper that it could be very simple. It could be like the hopping is done through some kind of enumeration between these channels, which fulfills all these constraints. Okay, we'll not get into the details, the mathematical details of this, but you are free to read the paper at whenever you have a chance. Okay. So we call this a virtual MAC protocol. Virtual MAC, again, it's like a sublayer. It's independent of 802.11, but it can actually lead to performance enhancement significantly. Okay, and what it does is that, of course, it divides the time into longer time slots. It's like a super frame. A longer time slot, like for 10 milliseconds at least, or 20 milliseconds. During this 10 or 20 milliseconds, you can have at least 10 to 15 packet transmissions during one slot. So it doesn't happen, the hopping is not, it doesn't happen at every packet. No, you take like a window of time, and the window is defined here as maybe like 15 milliseconds or 20 milliseconds. During that time, you can have 10, 15 transmissions. Okay? And then after that, you can switch to another channel. And after that, you can switch to another channel. So this allows parallelism for transmission. And during, again, this does not eliminate collision, because during the time of these 10 milliseconds, you may coincide with another channel which is used by other nodes, and in that case, collision may still happen. In fact, in that case, you can have a situation that you can tune to a particular channel, and someone is sending you on another channel, in which case you will not receive the transmission. There is some possibility that this could happen. Of course, they do the scheduling or the hopping in such a way that tries to reduce this, but there's no guarantee that it has zero possibility. Okay. The last slide, and we had to eliminate the break because he came late. Um, this is basically the ultimate degree of freedom. If cost is not an issue, then you can have multiple transceivers, in which case you can have each transceiver working either for sending or receiving on multiple channels at the same time. Okay, so you have a completely separate receiving circuit on multiple channels. So you can think of it as something like this. So on one node you can have one antenna, 2, 3, and each one would have its own receiving transmitter circuit. Okay, so this is the most complicated in terms of hardware design and of course the cost, but this will give you the ultimate degree of freedom, that this node, and this is usually done on the routers, wireless mesh routers. So you can transmit on these 3 antennas on 3 different channels at the same time. Okay, you can use one for receiving and one for sending. So full duplex. So you can send and receive at the same time on 2 different frequencies. Okay, and of course this is the ultimate flexibility, but the biggest challenge, because again you need to also schedule which transceiver uses which channel at any point in time, and that requires an end-to-end and distributed kind of scheduling on which transceiver. Now you have not only one channel at one single time, you have 3 channels. So you have 3 or 4 possibilities. So imagine the amount of possibilities that you have from one node to all the other nodes. So the complexity of scheduling these channels now become very, very high. Okay. According to the guy, there is a little work done on this area. Of course, now there is tons of work on this area, where you have a distributed wireless mesh network, and each node uses 3 or 4 different channels. So what channels should be used on what transceivers to send to which nodes in order to achieve global optimality? This is a very, very complicated problem, extremely complicated. It's obviously MP hard, and the combinatorial complexity of that problem is really high. So many people, they start to use some kind of heuristics and some kind of suboptimal and things like that, just to simplify the problem using certain assumptions and things like that. But we're not getting to the details of this, at least this time. I wanted to finish the MAC layer part to start talking about the routing layer next time.